Okay, this is chemistry, 9, 8, 14. So your percent composition is what you got divided by the mass of the entire original sample, because we're looking at what percentage of the original sample that ammonium chloride made up. If you had issues with that, you need to fix that. I think percent error calculations were pretty good in here. But the thing to remember is that percent anything is always part divided by whole. And the whole is the mass of that original sample that you had. Questions on that? Is everybody clear on that? Okay. Okay, so now we're going to resume with the Chapter 1 notes, finish those up, and then move on to some review time and time for homework. Okay, I believe we left our physics or our chemistry heroes here. We had talked a little bit about elements. We can take that roll of aluminum foil, tear it down until we're at a single atom. It's still aluminum. That single atom has all the same characteristics. Okay, so we'll back up to lab chemicals and purity. And we talked in the other class a little bit about salt. And you've seen my lovely chunks of salt from the mines under Lake Erie. You can pass this one around. It's filthy. It's disgusting. It's got all kinds of like ancient, dead, Paleozoic critter poop in it. It's got, body parts and mud and who knows what else. It's okay, you can touch it. And that's the way it comes out of the earth. Now, it can be refined down to the point where it is, this pure, white, granular crystal substance. And you've all seen table salt. We categorize chemicals by their purity in a couple different classes. So that salt that you're passing around, that's exactly how it gets mined out of the earth. And most of the salt of that particular mine gets crunched up and sold to municipalities, counties, etc., ODOT, and it goes on the roads that way. It doesn't matter that it's got everything under the sun in it. It still melts ice. So that starts us on the road towards industrial grade chemicals. These are things that are very impure. They may have big impurities in them, but you're doing large batch chemical processes, and some other little things in there don't really matter. Industrial grade chemicals are pretty rough very often. They have lots of atoms of other stuff in them. We can go all the way up to primary grade reagents. And primary grade reagents are the kinds of things, we purchase primary grade reagents, but even what we get is sort of like, typically school lab quality. If you go into primary reagent grade for like a pharmaceuticals lab, if you're making pharmaceuticals and there are atoms of something else in your reagents, those additional atoms may participate in chemical reactions beside the one that you want, which may mean that the drug that you're producing has unintended side effects. So this is one of the major issues you've heard about, like counterfeit prescription drugs. Well, I bought my prescription drugs over the internet. Well, great. And they could have been made in a lab pretty much any place in the world, and they could have been made in a lab using pretty shoddy, not primary grade reagents. So, that's the concern with those. And those are the different levels of purity that we talk about. Even actually food grade salt is less pure than reagent grade sodium chloride. There can be other things in your salt, little other atoms of stuff. It's not 100% pure. And that's just the way it is. But primary grade reagents are top in terms of purity. Okay, so elements, and you know this. We talked a little bit about compounds versus elements. Same characteristics, down to a single atom. Okay, so elements. We can take a chunk of gold. We can keep cutting it in half until we get down to a single atom of gold. It's got all the same characteristics that the big chunk did. Same for aluminum. Same for oxygen, though we don't typically think about oxygen as a solid. These are elements. And if you find it on the periodic table, it's an element. And what I've drawn here is the roughest periodic table ever, but I think you get the idea that that's what it is. If we look at the periodic table, starting here with hydrogen, and going across, just like you would read, and then coming back over here and reading the next row, and coming back over here and reading the next row, and coming back over here and reading the next row. It's arranged in order of increasing atomic number. Every time we step over one element, we add a proton. So we go from 1 proton to 2 protons to 3 to 4 to 5, 6, 7, etc. And it just steps up by 1 proton every time. It's not that hard. Okay, so now we're going to talk about 4 major types of elements. The first one is metals. And I'm going to say that most of this you have known certainly since middle school, and definitely, without any doubt, since physical science. The 4 broad categories here. Metals are the first kind of element that we're going to talk about. This is a general broad category of elements. And metals are good conductors of heat and electricity. They tend to be solids at room temp. They tend to have very, very high melting points, like thousands of degrees Fahrenheit, hence why they're solids at room temp. And they have these amazing characteristics. They're able to be pounded very thin and maintain their characteristics. And aluminum foil is our classic example. You can make a foil out of gold. You can make foils out of any metals. Some of them are less malleable than others. Gold and aluminum are 2 that are pretty easy. Silver foil is another good one. In the Middle Ages, there was a lot of gold leaf done in artwork, and you'll still see it in some churches, where it's actual gold that has been pounded until it is, just pretty much over an atom or 2 thick, and then applied to surfaces. That's gold leaf. Ductility is another characteristic of metals, and that allows them to be pulled into thin wires. And our entire economy and world and everything, a lot of things going on in this room depend on those wires. So copper's the big one. You can have gold wire. Gold's a great conductor. And if you buy high-end audiovisual equipment, if you go into Radio Shack, you can get AV hookups that have gold-plated ends, and they supposedly transmit better signal. I'm not enough of an audiophile to tell you that. So copper is one that our economy and the internet and everything else is dependent on. But metals are also some things you don't traditionally think of. Lithium is a metal, and it's something that's used medically in treating bipolar disorder. Sodium is a metal. So if you look at my, again, admittedly, rough outline of the periodic table, the first 2 columns are metals, and that whole middle section are metals. And we'll go into more detail with that. But the first 2 columns are where you have things like sodium, potassium, calcium. Calcium is a metal, okay? They're not things we think of as metals. We're more accustomed to seeing things like sodium and calcium and potassium in compounds where they don't look or behave at all as what we think of as metallic. But the pure elements, those are metals. Okay, non-metals are the second broad category of elements that we're going to talk about. Okay, so non-metals are everything that metals are not, and vice versa. If you have a sibling who you are nothing like, this is metals and non-metals. Metals are good conductors. Non-metals are lousy conductors. Metals are solids at room temp. Non-metals tend to be gaseous. Metals are ductile and malleable. Non-metals are brittle. Now, this is important. This is in their pure form and as solids. So oxygen is a non-metal. If I give you a balloon full of gaseous oxygen, can you describe that as brittle? No, it's a gas. Brittle is a characteristic of a solid. If we take oxygen and we cool it and condense it down to the point where it is a solid, which is some insane low temperature and high pressure, it would be brittle. So, carbon. How many of you can think of where you know of solid carbon? Coal. Diamonds, graphite. So the lead in your pencil is graphite, and it's brittle. It shatters easily. Coal shatters easily. Those are pure forms of carbon. Now, diamonds are very, very hard, but if you are able to shatter them, they're brittle. So they're kind of a weirdo. A lot of the nonmetals, now the nonmetals are by far the minority. If you look at, again, my crude depiction of the periodic table up here, the nonmetals are that last column and this little stair-step chunk over there. There aren't a whole lot of nonmetals. It's a smaller number. The metals are by far the majority of the materials we know of in the universe. A lot of these nonmetals are the things that you breathe in, and they form compounds that are important for life. I'm a pretty big fan of oxygen myself, and you're sitting in a pretty good soup of oxygen, carbon dioxide, carbon monoxide, nitrogen as the major component. So these are important, but minority. Okay, the metalloids. Neither fish nor fowl, the metalloids. Neither fish nor fowl. Okay, so metalloids. When I say they're neither fish nor fowl, they're not metals. They're not nonmetals. They behave like metals under some conditions. They behave like nonmetals under some condition. There's really just a handful of these, and this line doesn't even really do it justice because we should black that part out. The big one is silicone, and what I find interesting is I'm looking at the periodic table that we got from the Army recruiter. Silicone, I have never heard silicone referred to as anything other than a metalloid. This lists it as a non-metal, which I find kind of odd and kind of suspect, so argument against using those. Germanium and arsenic are other ones that are known non-metals. Your book lists boron as a non-metal. The Army periodic table lists it as a non-metal, or metalloid. Your book lists it as metalloid, and the Army periodic table lists it as a non-metal. So we'll go with your book as the reference. Silicone's the big one, and it's called a semiconductor. We talk about semiconducting chips. Semiconductors conduct under some conditions. They're not always conductors. They're only conductors sometimes. And typically it's conditions of heat and current. If you apply enough current to a semiconductor, it will transmit, but under that threshold it won't. And that's the basis of modern computing. Okay, the noble gases are the last of the broad types of elements. And they're important enough that they kind of get their own heading. They're not like anybody else. Okay, so the noble gases are sufficiently different. They get their whole own heading. They are group 18. I think I may have mistakenly included that with the non-metals in my little sketch. I'm doing thumbnail sketches up here. They're not terribly accurate. But the noble gases are that last column. They don't react. You're not going to find a compound of neon and something else. You're not going to find a compound of krypton with something else because they don't react. As one might guess from the name, noble gases, they are gases at room temperature. I know this is counterintuitive. And you are familiar, you have all probably seen some of them in action. So, gases do this cool thing when you add energy to something in its gaseous state. If you add enough energy, you can get those molecules or atoms to vibrate at a higher energy level and to actually give off light. Some of you I just saw take an upward glance. Now, the mercury that's in those tubes is not a noble gas, but it's doing the same thing. So we have mercury gas in those tubes under low pressure. You run current through it, electricity, and it glows. It gives off light. It's really pretty handy. Neon and argon and krypton and xenon all do the same thing, except they give you really pretty colors. And this is the neon lighting you're familiar with. And actually, neon itself is the orange, only the traditional orange. All those other colors you see are different noble gases in those tubes. And I'd have to consult a chart to say which was which. But the orange is neon. The other place that noble gases are really useful is in welding. So, do I have any welders? Okay, so we've got a piece of metal that we've just welded, and it's basically molten metal on the surface. It's very hot. It's got a lot of energy. It's very reactive. So here, we'll put our larger sheet of metal, and there's our seam that we've just welded. Yes, it's a useless, senseless seam. I just drew it. That's why. So, Metals that have a lot of energy, things that have a lot of energy, are more likely to react. Well, you've got a nice hot something that's got a lot of iron in it. Iron loves to react with oxygen in the atmosphere. What happens when iron reacts with oxygen in the atmosphere? Oxidation, which is going to make your nice pretty seam, rather than cooling to a nice gunmetal gray, it's going to cool to a nice rusty finish. Your hot metal is going to rust. If only there were some way to keep oxygen away from that seam while it cooled, or while you were welding it. Because the minute you take the flame away, it's going to cool pretty quickly. If you can prevent the oxygen from getting at the seam in that moment, you're good. So in a gas-shielded welding setup, you have your actual welder, and you're directing a stream of a noble gas, typically argon, at that seam. So that argon displaces the oxygen, and in essence you have a little bubble of argon on top of that hot seam, and that stream of gas cools it and protects it from reacting with oxygen. So rather than rather than cooling and rusting, your seam cools to a nice solid metal finish. So it's very useful, and if you know anybody who welds, or you have a chance to go someplace where they do some welding, if they have argon tanks outside, they are doing gas-shielded welding, because that's the only reason to have argon tanks. They actually distill that from the atmosphere at one of the plants down in West Virginia, where we get liquid nitrogen here. They pump it right out of the atmosphere, and it's up there at like, I don't know, point something % of the atmosphere. There's not a lot of it, but if you pump a lot of air through the compression chambers, you can extract that argon. That's it, folks, for Chapter 1 notes. So, the rest of this time you have to work on the labs if you're not done with them. You have to work on the homework if you're not done with that. You have to ask questions specifically about homework problems or test stuff.